With Victory Engineering. I just wanted to share with you a recent project that we had. I'll go ahead and apologize ahead of time. I don't have a tripod. I'm not a camera guru, so I'm doing this one-handed here. So, latest project was we've been building a vacuum form machine, and we needed to drill thousands of holes in this big aluminum plate on our vacuum former, on our CNC router. And so the tiny holes we'll be drilling is perfect for our spindle. We'll be drilling 60 thousandths holes, so we can spin at about 12,000 RPMs, no problem. But I got to thinking, if we wanted to drill bigger holes, which we do for the mounting holes of the vacuum platen, we'll need some significantly larger holes, maybe 1/4 inch or so, maybe 5/16, and our router probably doesn't want to spin at a few hundred RPMs or even 1,000 RPMs for that matter, because it just doesn't have any torque that low. So I picked up this air drill off of eBay. It's a DeSouder brand. I thought about just buying air drill or air impact off of at a Harbor Freight or something, and making a clamp to clamp to my spindle like a lot of people do. But I wanted something a little bit sleeker and maybe more designed for this type of drilling. So anyways, pick this guy up. The clamp that I want to use, I knew I wanted to be concentric, so I don't have to worry about any offset tooling in my G-code. So basically, it's going to hang concentrically underneath my spindle here, like this. And so the easiest solution I could come up with that was also very strong was my spindle up here protrudes down below my linear rails. They're part of my Z-axis here. And so I also have a little bit of a lip on my Z-axis rail before I bottom out on the collar up here of my spindle. So I knew I wanted to use that as an anti-rotation feature for my coupler. And so this is pretty big here. I'll set this on this plate down low. Pretty big here, a little over a couple inches, maybe 2.5 inches. And then I wanted it to neck down somewhere in here and then go over my spindle. And then the spindle has these mounting flanges, this mounting flange with mounting holes here. So I knew I wanted to come up through those and into my coupler for an anti-rotation feature on the drill to keep it from spinning in the coupler. So the first iteration went great. Took me maybe, 4 or 5 hours to design after going through a couple iterations. Took 28 hours to print and printed out of ABS. We've had a lot of luck printing in ABS lately, especially with some bigger parts, because we've done a lot of testing in different speeds and different temperatures. I'll show you in a minute, but we have a heated enclosure now, so that's helped out a lot. So here it is. It's about 8.5 inches tall. It's an inch thick all the way around. Here's my flats on top for anti-rotation. I put an 1/8 inch slit down the middle so that when I clamp it, clamps tightly around both the spindle and the air drill. So I have flats here, so I can just simply stick a bolt through, and then a nut and a washer on the other side. Or I was going to make a flat plate that went all the way down, and then it has 3 holes in it for the top, and then of course the same for the bottom. I've got 7 holes down through here for some 1/4 inch screws. So here's the anti-rotation feature. Let me get the lighting right here. Feature on the bottom. I did a pretty generous 60-degree sweep right here, so I didn't have any overhangs, so I didn't have to worry about printing support material. So yeah, it worked out great. It was a little tight in this hole and in the hole in the bottom. I had to kind of pound it in there with a dead blow. So I opened up 40 thousandths. I'm not sure exactly how the next one's going to fit, but so let's look at it. I made a few design changes. Here's the enclosure, and there it is. It was printing overnight. Says it took 40 hours and 40 minutes. I don't know if oh no, it didn't. It says 32 hours and 30 minutes. So a little over 30 hours. So let me open the TAS 5 up. So there it is, holes printed in it, and this time I kept it the shape of it concentric and ran some hex profiles in there just to drop some screws in. So let me move this thing. Okay, let's see how this thing comes off. I used some Elmer's, is it Elmer's glue? Yeah, Elmer's glue on my build plate, and then I've been printing a brim around it, and that's helped as well. Let's see how this thing breaks off. Golly, I'm pulled awful hard. Okay, there it goes. Great. So here it is. I haven't touched this part yet. Been anxious to come in here and do it, so seeing it the first time with you. There's my hex holes that I'll drop my nylon insert quarter 20 nuts in, and then the same for my socket head cap screw with a 1/2 inch diameter washer. So I'll get this cleaned up. I'm going to take my deburring tool and clean this brim off, and maybe even get the drill mounted in here and let you know how it fits, and get the hardware in here, and we will see how this thing fits up on the router. Let's just show you the design of the coupler. Again, this is the second iteration, so yeah, not much obviously different than what you see over there. So designed it here in SolidWorks. It's just got a couple different feature groups here. We've got the upper clamp area, lower clamp area, the flange mount area, and then the main profile was just a revolve feature that I used that had a profile. So yeah, it's pretty simple, but also looks pretty cool. And so I'll bring up now the software for the 3D printing, and I'll just go ahead and pull the file into here so you can kind of see what it looked like. Okay, so one thing I need to fix is the scale factor. When SolidWorks exports an STL, it does not export it in inches, it exports it in 1 millimeter. So I've got to do a 25.4 to 1 ratio for the scale. And let me rotate this. Yeah, so this is how we did it. Looking at the machine criteria, we've got layer height of 0.15. It's pretty coarse, but we wanted to make sure that we didn't spend 40 hours or 50 hours instead of 30. 1.5 millimeter shell thickness, which is of course 3 times our nozzle diameter. We did a 25% infill with a 0.45 bottom and top thickness. That's 3 times. We wanted to make sure we got a pretty good thick layer on the top and bottom. We did 90 millimeters per second on our print speed, 245 degrees Celsius on the temperature. We went down a little bit. We were at about 250 to 255, but we noticed some strings in between the prints, and we thought it might be too hot. So, and then a bed temperature of 105. We did not have support material, so that's a default on for us. We did have a brim, and let me bring up the brim line count. We did a 20 line count, so that seemed to help a little bit with the warping. Going over to our advanced settings, we had a nozzle size of 0.5. Retraction is 25 millimeters per second and a distance of 1.25. It was a distance of 2 millimeters, but we noticed it was retracting too much, and the rapid speed in which it retracted it and pushed it back down was biting into the material, and it was eating it up and started missing steps. So then we slowed the retraction rate down, and then doubled the print time. So this seemed like a happy, healthy medium, so to speak. Some of the other settings we didn't change too much from the last job. Our travel speed's 100. We don't have the cooling fan on. We noticed that we get a little bit of warpage when we try to blow the cooling fan on. And then the last bit of machine settings here that we have under the expert settings that we tweaked a little bit is, let's see what a few things that we messed with. Brim line count, of course, I showed you a minute ago. The skirt. Skirt distance and line count. I didn't print the skirt for some reason, but that's something that typically helps us to make sure that the plastic's flowing before it actually starts printing. So yeah, that's the settings that we had for the printer, and then I'll turn it on layer mode here, and you can kind of see it show the visualization of the toolpath, and you can see that there's 1,398 layers. That's why it took about a little over 30 hours. There's quite a bit of layers. Not going super fast at 90 millimeters per second. And the 0.15 layer height could be increased a little bit. One thing that would speed the part up is drop the fill density from 25, but we noticed when we get below about 20, the walls in between in the shell density are a little far apart, and we get a little sagging in the plastic from one wall to another. So yeah, this is what it looked like. I can kind of scroll down through here and kind of start from the bottom and work my way up. So just in case you're not familiar, the fill density is this honeycomb in the middle. So the diameter of the square is has dependency on the fill density. So the lower the fill density, the bigger diameter that square is, and the more voided space you have in there. But of course, the wider that square gets, you're then having to drape plastic across it once you get to other features. And so, for example, the top, or even some of the holes, for example. So let's say I'll go up here, and so you can kind of see as it starts to make this hole here, it had to, let me go down a little bit. As it starts to create the hole, then of course you have to drop the plastic over that fill density. So we found 20 or so is good. I wanted this one a little thicker because I knew I was going to be putting stress on this part, so I went 25. So yep, that's it. That's all the settings there. So I've showed you the design, showed you the G-code and CAM generated from Cura, the 3D printing software, and now we'll go look at the part and get it and put together with the hardware. Thanks for watching.